Hi, let's talk about mass and weight. The unit of mass is kg and the unit of weight is Newton. That's all for this video. Bye bye. Okay, I'm just joking, but looking at their units, you can actually tell what they are already. Right now, I would like you to pause the video, go and check out the textbook chapter 2.09 on page 42, and you should be able to fill in all the answers on page 15 here. So pause the video and do it now.
A few moments later.
Okay, so let me go through this page with you. First of all, for mass, it is a measurement of the resistance to the acceleration. So if you recall what you learned earlier, F equals to ma. If you have a greater m with the same amount of force you have, then obviously acceleration will be smaller. So that's why if you try to push a greater mass, is harder to push. I mean, imagine you push someone who is heavier, it's way harder to push than say your textbook or my cup, for example. So you may wonder, how come there are things that are of bigger mass or smaller mass? What's the difference between you and me so then our mass will be different? Fundamental idea of mass will be contributed by the amount of atom you have. If you think about the kinetic theory you have learned in probably junior secondary, then we talk about for different state of matter, gas, liquid, and solid, they are of different pattern of the atom. At the same time, for an object, they will have a finite number of atoms, even though an atom is very small, but then it's not infinite, of course. So depending on how many atoms you have, and of course there are some other consideration, as in for each atom how heavy they are, and so all these add together, you will be able to find out, or evaluate the mass of an object. For example, I just had my hair cut, so technically I have a little bit less mass. While for the weight, it is an interaction between the bodies due to their mass. So as long as you have mass and another object has mass, then you have weight, you have gravitational force basically. Of course, the most common weight or gravitational force that we talk about in physics will be between an object to the planet. So probably will be the Earth that we are talking about. And again, you can tell from the unit because it is in Newton, and therefore weight is a force, and therefore force is a vector, and therefore weight is also a vector. Meanwhile, for mass, it is a scalar. You can't say I am 70 kg upward or downward or left or right. There's no direction for mass. While for weight, there's direction, is pointing downward towards the planet. But of course, if you're talking about, say, two planets, for example, the Earth and the Moon or the Sun, then their weight, or more precisely, gravitational force, will be pointing towards each other. So there's nothing called downward in that case. We'll be pointing towards each other directly. And so for us, because we are somewhere on the Earth, for example here, and the weight is always pointing towards the center of the Earth, and therefore to us it kind of always downward, but that is not exactly true, because if you take the plane to just another spot on Earth, then you'll find out the force is no longer in the same direction because the Earth is round, just so you know. So the formula that link mass and weight together will be W equals to mg. Namely, in work formula, that is weight equals to mass times gravitational field strength, which is something that we'll talk about now. Gravitational field strength is kind of straightforward. If you look at the unit, it is Newton per kg. So for Earth, it's going to be 10 Newton per kg when you are on the surface, or more precisely 9.81 Newton per kg. 9.81. Does it sound familiar to you? Yes. Gravitational field strength can be taken as gravitational acceleration. They are equivalent. Well, let me tell you why later on, but then here, when we go back and see Newton per kg, for Earth again 10 Newton per kg, that means if you have 1 kg of mass, or an object have 1 kg of mass, then the gravitational force, as known as the weight, would be of 10 Newton exactly. Okay, Newton is here. And if your mass is 60 kg, right, and then your weight under the Earth's surface will simply be, guess what, 600 Newton. And that's the idea of Newton per kg. That means for every kg of mass, you have 10 Newton or 9.81 Newton. Alright, so back here, so how come the gravitational field strength would be equal or equivalent to gravitational acceleration then? Think about the case in free falling. So when you apply F equals to ma, that's Newton's second law, F being the net force. However, the net force is simply weight when you're free falling, because that's the only force that's dragging you down. So we can put down W equals to ma. At the same time, you can refer back to the definition of W equals to mg here. And so you can technically change the W into mg. Okay, so for simplicity, I'll just write like this. And you'll find out the m can cancel out. So eventually, g equals to a, which is the acceleration that you have when you are free falling. And in fact, this is exactly how Galileo's experiments can be concluded. You can see that no matter what object you have, no matter what mass you have, as long as there's no air resistance, of course, then your acceleration is simply defined by the gravitational field strength of the planets that you are on. Amazing. Speaking of the moon, if you recall, previously I played you a video, that is this one, and if you try to compare that free falling on moon to the one that is on Earth, the one that is on Earth takes much less time to reach to the ground with the same height. And that's something to do with the gravitational field strength. And so the gravitational field strength of the moon is much less simply compared to the Earth. More precisely, one number that you can remember, the gravitational field strength on the moon is only 1/6 of the Earth. And so this is because the moon is much less mass. I'm not sure if this is the right word to say. The mass is much less compared to the Earth. And that's why the gravitational field strength is much less, and therefore the gravitational acceleration is much less also. Physics may concern you for 2 years for IGCSE, and if you pursue IB also, then that will be 4 years, which I will be happy. Or if you really feel the passion of learning physics, then that will be a concern for your whole life. But there's also another question, I think, for everyone that you will be concerned for your whole life, and that is, how do we actually lose weight? I want you to think about it and put down as many approaches as possible right here. So please pause the video now and write down your answers. Alright, so you may have put down different approaches. For example, like I said, you may simply cut yourself, cut your hair. You could go for excretion, like poo or pee, get things away from you, literally. And you may also say, oh, eat less, probably. But the most scientific way of saying how you actually lose weight, more precisely you are losing mass, not losing weight, is think about what you learned in junior secondary for respiration. In respiration, you learn about there is a chemical formula. Do you know what it is? The answer is something to do with glucose C6H12O6, and you need to intake oxygen, so O2, and you breathe out CO2 as a product of the chemical equation. You got H2O. Alright, and while you may talk about how to balance the equation, because you have 6 carbon here and only 1 carbon here, so therefore you have to multiply this with 6, and so on and so forth. 6 here and 6 here. So this is how you balance the equation. Okay, enough chemistry and biology for now. The point I want to make here is, think about this. This is what you have in your body. Starch is what you have in your body. So that will be part of your mass. Oxygen you intake from the atmosphere, so it doesn't count. And then for CO2, when you breathe out, it's gone, right? It's out of your body. Then if you compare these two, obviously CO2 is going to be heavier than O2. Well, for H2O, yes, it still stay in your body. Of course, H2O is much easier that through pee and also sweat as well, that you get it away from your body. So this is the reason how you lose mass or lose weight, right, in the most layman term. And that's why when you try to look for those tips for like how do you actually lose weight, online, YouTube, whatever, they will ask you to do cardio exercise, right? Because that is the only way that can increase your heart rate, and that means you basically will burn more starch by intaking more oxygen, and that is performing this chemical reaction as many times as possible. In fact, I'm not sure if anyone thought of it. There's also another approach, and that is simply move to another planet. Think about this. When we try to say lose weight, I mean, if you really talk about weight in physics, that is governed by the equation W equals to mg. I mean, if I have no control of my mass, at least I can control the g if I could go to another planet, for example, moon. So here is a challenging question for you. If someone go to the moon with the scale, I don't know why, he or she brought the scale with him or her, but then the reading is actually 70 kg on moon, remember. Then there must be something wrong, because obviously on moon you should weigh less, so it shouldn't be 70 kg. So my question is, what would the reading be when that person bring the same scale back to, I mean, it doesn't really matter which scale, but then when he or she try to weight himself or herself on the earth, what reading should they give? Pause the video and try to do the calculation.
A few moments later.
Okay, in order to do this question, you have to understand two things first. So the first thing is, how does the scale work? Think about this. The scale doesn't really read your mass. Think about this. On Earth, if I am really 70 kg, then of course my weight is going to be 700 Newton that is pushing onto the scale. And of course, if you think about the scale, then that's the force that it's experiencing. And therefore, internally, by calibration, then it will read you 70 kg. But of course, when people try to create a scale, we expect you to use it on Earth. We don't expect you to bring it to another planet and use it. And therefore, the scale would not know that we are on moon. And so this is the conversion that it will give you. It doesn't really about your mass, it's more about the force that it's experiencing. For example, if you somehow take up a cat, I am not good at drawing anything, and say the cat is, say, 10 kg, okay? In this case, the total weight that you both have will be having an extra 100 Newton, and that is of 800 Newton right now. And therefore, the scale, I mean, under your feet will be showing, instead of 70 kg, it show 80 kg, okay? Because the force adding onto the weight, I mean, the scale will be 800 Newton. And so using this logic, and imagine if you are on moon, having the scale, and you step on top of it, the reading is 70 kg. That means the force that you exert onto the scale is going to be 700 Newton. But then that is according to the gravitational field strength on moon. So that is W equals to mg, W being 700, while mass is the unknown. G, if you remember what I said, it is 1/6 of the Earth. So we could take it as 10 divided 6, or if you go to Google it, that's fine too. And so by doing the calculation, you will find the mass going to be, oh my god, 420 kg. Then there must be something wrong with your body in this case. Lastly, there are 3 multiple choice questions from the past paper, so I would like you to try it out. Please pause the video and find out the answers.
A few moments later.
Okay, first question, which of the following statements is correct? Mass and weight are different names for the same thing? Of course not, right? Otherwise we don't bother to have this video. Mass of an object is different if object is taken to the moon. No, right? Mass is always the same. Just like what we said, if you are 70 kg on Earth, you are also 70 kg on Moon. It's just the weight are different. So C, weight of a car is one of the forces acting on the car. Yeah. It sounds quite strange, but yeah, it's true. D, weight of the chocolate bar is measured in kilogram. No, of course not. It's in Newton. Okay, you may want to write it down like this, Newton. Question number 2. 1 kg sample of aluminium in different lab, same town, 1 kg sample of iron, which is always having in common same density? Of course not. Density depends on the material, so they are not the same material. Same temperature, maybe, depends. Really, I mean, depends. If you switch on aircon, then they could be different. Volume is not, because they are already not the same density. Then since they are the mass are the same, therefore the volume would not be the same. Think about the equation that you learned about density. Density equals to mass over volume, and so if the mass is the same, but then the density is different, so for example one is bigger than the other, then the volume would then be smaller than the other. So that's the relationship that you may have. D is saying the same weight, and that is of course D will be the answer, because W equals to mg, and if you have the same mass, and since you are on the same town, not even the town, I mean if you are even on the Earth's surface, they could be like US and Hong Kong, like New York and Hong Kong for example, the G is more or less the same, so it's unchanged, and therefore the weight will be the same. This reminds me again the IQ question about whether 1 kg of iron is heavier or 1 kg of feather is heavier. Last question, you have got a mass with 10 kg on these 5 different planets, and these are their weight. So which one would have a smaller weight than on Earth? Okay, so I don't get it. Isn't it just the one that is with less weight? Then that means Mars, Mercury, Venus. So Mars, Mercury, Venus, then that's B simply. You can even work out the gravitational field strength by using the equation W equals to mg, and therefore Mercury should be of 4 Newton per kg, Venus should be 9 Newton per kg, similarly for Mars would be 4 Newton per kg. Okay, so in this video you learned about the definition of mass and weight, the equation weight equals to mg, and also the idea of gravitational field strength. And more importantly, now you can explain to other people how people actually lose weight. I hope you enjoy learning physics, biology and chemistry with me today, and if you do so, please hit the like button now and subscribe to my channel. I'll see you again in the next video. Bye.